Namaste. Me, Taravir Shrestha. I would like to welcome all the students of class 10 in this session. Subject of this session is Science, class 10, chapter 1, force. Dear students, we have found some information about gravitation and force of gravity in the previous lessons or previous session. Today we are going to discuss about another subtopics under this chapter force, which is acceleration due to gravity. When an object is released from a height, it falls downwards due to the attraction of the force of gravity of the earth. As it falls downwards, its velocity goes on increasing. It means its velocity changes for time under the action of gravity, and it produces an acceleration, which is called acceleration due to gravity. In the absence of the air resistance, the acceleration produced by the force of gravity can be defined as the acceleration produced on a freely falling body under the influence of force of gravity, and it is denoted by small g, and its unit is meter per second square. It is an example of uniform acceleration. Now let us go to the next point. The speed of freely falling body goes on increasing at a uniform rate as shown in the figure. Look at this figure. While an object is symbolized by an apple, was it raised at first so that its initial velocity is 0, u equal to 0, and it is released immediately, and it covers 9.8 meter in the first 1 second. That means its velocity v1 becomes equals to 9.8 meter per second. Again, in the second 1 second, it covers 19.6 meter distance. It means its velocity v2 becomes 19.6 meter per second. And in the third 1 second, it covers 29.4 meter distance. It means its velocity v3 becomes 29.4 meter per second. It gives the uniform acceleration, which is equal to 9.8 meter per second square. It is experimentally verified by the senior scientist. Okay. Now, the acceleration due to gravity near the surface of the earth is found to be 9.8 meter per second square. It is a uniform acceleration due to gravity. Now, which body, whether heavier or lighter, one falls faster? What do you think? Please make a mind. According to the pioneer philosopher Aristotle, heavier one falls faster than lighter body. It is the ancient thought, and generally, the most of the people think like this. But this concept was disproved by Galileo Galilei in 1590 AD, and proved that all the freely falling bodies, whether heavier or lighter, fall with the same speed. For this, Galileo Galilei had performed a series of experiments, and once he took two iron balls of different masses and dropped from the top of Leaning Tower of Pisa simultaneously, and he found both of them reach to the ground simultaneously, and he proved this, that all the bodies, however the mass will fall at the same speed downward and reach to the surface at the same time if they are released from the same height at the same time. Let us go to the next. To prove this theory, Sir Isaac Newton also perform experiment. And generally, while very lighter body and heavier bodies are being dropped from a same height simultaneously, the heavier one will fall faster than the lighter one because of the air resistance. But while there is no air resistance, then it is found that all of the bodies, whatever be the masses of the body, fall at the same rate, which is proved by Newton as experiment shown in the figure. Newton had taken a feather and a coin in his experiment, and he put these objects in a long, wide, closed glass tube provided with a vacuum as shown in the figure. And this is the feather, and this is the coin, which were at the bottom of the tube. And he had inverted it quickly so that this is shown like this figure number 3, where the coin fell more quickly than the feeder in this condition because there was air inside the tube. And then again he re-inverted the tube, and it again the feeder and the coin lied at the bottom of the tube, and he removed all the air from the tube by using the vacuum pump, and he quickly inverted the tube, and thus he found that both of the object, coin and feeder, falls together downward because of the same acceleration due to gravity and in the absence of air resistance, that is vacuum. And he had proved that in the vacuum, it means in the absence of air resistance, all the bodies, whatever be the mass, fall at the same speed under the influence of gravity. This proves that all the bodies, whether the body is heavier or lighter or bigger or smaller, fall with the same speed downward under the influence of gravity only if there is the air resistance is neglected. Now, let us go to the next. We can calculate the acceleration due to gravity of the Earth, and thus we have to derive the formula of the acceleration due to gravity of the Earth. Let us go to derive it. Later, the mass of the mass and the radius of the Earth, P, M, and R respectively. An object of mass m is supposed to be lying on the surface of the Earth as shown in the figure. This is the mass of the Earth, which is written m, this big circle-like structure, that is the sphere, and this small body which is lying on the surface of the Earth is denoted by small m. This is the small object lying on the surface of the Earth or near to the surface of the Earth, and the distance between the Earth and the object is denoted by it's taken equal to the radius of the Earth r, because the distance between the center of the Earth and the object is equivalent to the radius of the Earth. According to Newton's law of gravitation, the force of attraction between them is given by F equal to capital G, capital M, M by R square, where capital G represents the universal gravitational constant, capital M represents the mass of the Earth, and small m represents the mass of an object lying on the surface of the Earth, where R represents the radius of the Earth. It is taken as equation 1. On the other hand, we have learned in class 9, according to the Newton's second law of motion, the force of attraction, which is the Earth attract the object towards its center, is given by F equal to mg. Mg, that is m is the mass of an object which is being attracted towards the surface of the earth, and g is the acceleration due to gravity. Uh, and it is taken as equation 2. Now we can combine equation 1 and 2. We get mg equal to gmm over r square, where m and m on left and right will be cancelled, and thus we get g equal to gm by r square, which is the formula used to calculate acceleration due to gravity of the earth, and it is denoted by equation 3. This shows that the attraction due to gravity g, acceleration due to gravity g, is independent of the mass of an object m, which is being attracted towards the center of the earth. Since the value of g and m, that is g is the universal gravitational constant and the mass of the earth m are constant, but radius of the earth r is variable on the surface of the earth due to orange shade. Then we get g is inversely proportional to r square. That is why acceleration due to gravity is inversely proportional to the square of the radius of the earth. Due to this fact, the value of g of the earth varies slightly from place to place on the surface of the earth. Like the radius of the earth at the equator is longer than the radius of the earth at the pole. That's why the value of the acceleration due to gravity at the equatorial region of the earth is 9.78 meter per second square, whereas the value of the acceleration due to gravity on the surface of the polar region is about 9.83 meter per second square. And thus average value of acceleration due to gravity of the earth is equal to 9.8 meter per second square. Dear students, I hope you can do this derivation and apply this formula g equal to gm by r square for the calculation of acceleration due to gravity of an object near to the surface or on the surface of the earth. Let us go to next. The acceleration due to gravity depends on the mass of the heavenly body like the earth and the radius of the heavenly body, so that it varies with the factors of acceleration due to gravity. Here we discuss about the variation of acceleration due to gravity with height from the surface of the earth. Let m and r be the mass and the radius of the earth respectively. The value of acceleration due to gravity on the surface of the earth is given by g equal to capital G capital M by r square, where g represents the universal gravitational constant and m represents the mass of the earth, and that r represents the radius of the earth. This is the general formula used to calculate the value of acceleration due to gravity small g. It is taken as equation 1. If g1 is the acceleration due to gravity at a height h from the surface of the earth, we have g1 equal to capital G capital M over r plus h whole square, where r is the radius of the earth and the object is placed at a height of h shown in the figure. Look at here. This is the radius of the earth, m is the mass of the earth, and from the surface the object is placed at the point P, so that the height of the object from the surface is, so that the total distance between the center of the earth and the object becomes r plus h. That's why the formula to calculate the acceleration due to gravity at the height h from the surface will be capital G capital M by r plus h whole square. It is taken as equation number 2. Equation number 2 gives the acceleration due to gravity of earth at a height h. Now From these two equations, 1 and 2, let us divide equation 2 by 1 side by side. We get G1 by G equal to Gm by R plus H whole square over Gm by R square, and this Gm and Gm will be cancelled. That's why G1 equal to R square by R plus H whole square into G. And this gives us the G1 equal to R by R plus H whole square into G. It is taken as equation 3, and this G1 equal to R by R plus H whole square into G gives the relationship between G1 and G. That means the acceleration due to gravity on the surface of the earth and the acceleration due to gravity at any height A will be related with this relation. Equation 3 gives the relation between the acceleration due to gravity of the earth on the surface and at a height h, where R by R plus H whole square is lesser than 1, and thus G1 is lesser than G. That means the acceleration due to gravity at a height h will be always lesser than the acceleration due to gravity near to the surface of the earth. From this relation, we can calculate the acceleration due to gravity at any height. Okay, dear students, from this relation, we can conclude that the acceleration due to gravity decreases with the height or altitude. Now, I have submitted some workout examples. Number 1, what is the acceleration due to gravity on the surface of the earth when its mass is 6 into 10 to the power 24 kg and radius is 6,380 kilometer, given G equal to 6.67 into 10 to the power minus 11 Newton meter square per kg square. Let us solve it. Solution here. Mass of the earth, capital M, is equal to 6 into 10 to the power 24 kg. Radius of the earth, capital R, is equal to 6,380 kilometer. That is to be converted into meter. So that it is equal to 6,380 into 1,000 meter. And we can write in power of 10, it is equal to 6.38 into 10 to the power 6 meter, because the meter is the SI unit of distance. Now we have to calculate acceleration due to gravity, G equal to what? We have the formula G equal to capital G capital M by R square, where G is the gravitational constant, M is the mass of the earth, and R is the radius of the earth. That's why it is equal to 6.67 into 10 to the power minus 11, which is the value of gravitational constant, and 6 into 10 to the power 24, which is the value of the mass of the earth, over 6.38 into 10 to the power 6 whole square. This is the radius of the earth in meter, which is equal to 6.67 into 6 into 10 to the power 24 minus 11. Mark here. When there are the powers of 10 in the form of multiplication, then the powers will be added. And here 11 is in negative form, so that 24 minus 11, 10 to the power 24 minus 11 under 40.7044 into 10 to the power 12, which is equal to 40.02 into 10 to the power 13 by 40.7044 into 10 to the power minus 12. This 10 to the power 12 is carried to the numerator, which becomes the power negative, and thus we get 40.02 over 40.7044 into 10. which is equal to 0.983 into 10, and thus this is equal to 9.83 meter per second square. Therefore, the value of acceleration due to gravity on the surface of the earth is calculated g equal to 9.83 meter per second square. Let us go to the next example. What is the acceleration due to gravity of the earth at the peak of Mount Everest? When the mass and the radius of the earth is 6 into 10 to the power 24 kg and 6400 kilometer respectively, g equal to 6.67 into 10 to the power minus 11 newton meter per kg square. This is the numerical problem related to calculate the acceleration due to gravity at any height from the surface of the earth. The solution is given mass of the earth capital M is equal to 6 into 10 to the power 24 kg. Radius of the earth capital R is equal to 6,400 kilometer, which is converted into meter at 6.4 into 10 to the power 6 meter. Height of Mount Everest, we know, is equal to 8848 meter, and acceleration due to gravity g equal to what? We know that the formula of acceleration due to gravity at any height, g1 equal to capital G capital M by r plus h whole square. R plus h whole square, and the value of capital G is 6.67 into 10 to the power minus 11, and the value of M is 6 into 10 to the power 24, where the value of R is 6.4 into 10 to the power 6 meter plus 8,848 meter whole square. Now, this 6.67 into 6 into 10 to the power 13, that is 24 minus 11, 13 over 6.4 into 10 to the power 6 plus 0.00848 into 10 to the power 6 whole square. Here the value of height of Mount Everest, 8,848 meter, is converted into kilometer, where we can add this height, radius of the earth and height of Mount Everest, changing into the same powers of 10. That becomes 40.02 into 10 to the power 13 over 6.40848 into 10 to the power 6 whole square. Now this gives 40.02 over 41.073 into 10 to the power 13 over 10 to the power 12. This gives us is equal to 0.974 into 10 is equal to 9.74 meter per second square. That's why the acceleration due to gravity on at the peak of the Mount Everest is g1 equal to 9.74 meter per second square. Dear students, you can calculate the acceleration due to gravity at any height according to the given data. Dear students, now you can solve the numerical problem given in your textbook, page number 29 and 30, as well as in journal book, page number 19 and 20. Dear students, I am going to end this session for today. See you in the next session. Thank you very much.